And welcome back. The topic for this week is going to be sampling and sampling distributions, where we'll start to see how what we've learned about probability can help us to use samples to understand the broader world around us. As always, first things first, we'll start with a recap of last week's activity. In last week's activity, you are asked to use a probability distribution to find the probabilities of different outcomes and to answer some questions. We'll answer these questions on the document camera.
So for our activity 6 setup here, we know a couple things. We know that our jury trials have an average of 4.2 days, a standard deviation of 0.9 days, and a normal distribution. So we can draw the probability distribution for the length of a jury trial as looking like this. We've got our normal distribution bell curve shape, and we've centered our mean at 4.2. The other thing I'll add to this graph are these tick marks for 1, 2, and 3 standard deviations away from the mean. And we can fill in these values with our knowledge that the standard deviation is 0.9 days. So for each one, we're going to either add 0.9 going in a positive direction, or subtract 0.9 going in a negative direction to fill in the values. So 4.2 plus 0.9 brings us to 5.1. 5.1 plus 0.9 brings us to 6.0. 6.0 plus 0.9 brings us to 6.9. So each of these then corresponds to the mean, plus 1 standard deviation, plus 2 standard deviations, and plus 3 standard deviations. We'll do the same thing going in a negative direction, so we'll subtract 0.9 from 4.2. Doing this will give us 3.3, 2.4, and 1.5, which correspond to -1, -2, and -3 standard deviations away from the mean. So now we have a couple questions to answer. We can answer the first two using just what we have written up here. So what are the probability of a trial, or what is the probability that a trial will last between 3.3 and 5.1 days? And we can say we have a 95% chance that a trial will last in what range of time. Our first question we can answer using the 68, 95, 99.7 rule. We know that we will always find 68% of the area under the curve within the mean and plus or minus 1 standard deviation on either side. We know that 3.3 and 5.1 correspond to the mean minus 1 standard deviation and plus 1 standard deviation on either side. This tells us that we will always find 68% of the area under the curve between those two values. Therefore, we have a 68% chance that a trial is going to last between 3.3 and 5.1 days. So the answer to this first question here is that we have a 68% chance that our trial is going to last between 3.3 and 5.1 days. Again, because 3.3 and 5.1 correspond to this mean plus or minus 1 standard deviation. So our answer here is just 68%. There's a 68% chance that the trial is going to last 3.3 to 5.1 days. We can also work backwards, go in the other direction, and we can say that there's a 95% chance that a trial is going to last whatever values correspond to the mean and 2 standard deviations on either side. So in this case, we're taking the second part of our 68, 95, 99.7 rule, and we're working backwards. We know we need the mean plus or minus 2 standard deviations. We can find plus 2 here and minus 2 here. This tells us that the values that correspond to these are the values that correspond to a 95% chance of obtaining an outcome in that range. So here, if we go out 2 standard deviations on either side, we've got this total shaded area here. We know, based on the rule, that there's a 95% chance of getting an outcome within this range. So we can look at the values that correspond to -2 and +2 standard deviations away from the mean, which are 2.4 and 6.0, and we have our answers. So we've got a 95% chance that a trial is going to last between 2.4 and 6.0 days. And that's our answer to number 2. Our next two questions involve the use of z-scores and the z-table. So the first thing we'll do here is we'll calculate z-scores for 3-day and 7-day trials. Our z-score equation looks like this. We're going to take our value of interest, whatever that is. we're going to subtract the mean for the probability distribution and divide by the standard deviation for the probability distribution. So for a 3-day long trial, we'll plug in 3 for our value of interest. We'll plug in our mean, which is 4.2 days, and we'll plug in our standard deviation, which is 0.9 days. If we do this, we end up with negative 1.2 over 0.9, and this comes out to about negative 1.33 if we round it off. We can do the same thing for a trial of 7 days. We'll plug in 7 as our value of interest, subtract 4.2, divide by 0.9, and if we do all this math, we end up with a z-score of about 3.11. So our z-scores for 3 days and 7 days are negative 1.33 and 3.11. So that's the answer to our third question here. On to our final question. What's the probability that a trial is going to last between 3 and 7 days? I'm going to redraw our distribution here and shade in our values of interest. So we are centered at 4.2. We want to know the probability that a trial is going to last between 3 days and 4 days. So we can draw a line for 3 right around here. We can draw a line for 7 right around here. If we use a z-table, we can look up the probabilities that correspond to these z-scores. And if we recall, the z-table looks something like this. And it shows us the area under the curve between a mean on a standard normal distribution and a z-score on a standard normal distribution, where that standard normal distribution is exactly the same as the one we started with, except that now we're counting in z-scores, rather than, in this case, days. So we can redraw our distribution. It'll look exactly the scale. The lines are going to fall in exactly the same place. We're going to have exactly the same amount of area under the curve shaded, but instead of counting in days, we're counting in z-scores, so it looks like this. Now, using our normal distribution, or sorry, our z-table here, and our normal distribution, we can look up the area under the curve to the right of the mean and to the left of the mean. And by combining these areas, we can find the total shaded area on this standard normal distribution, which will be equal to the total shaded area we're interested in on this regular normal distribution. So on my z-table here, I'm going to look up the area under the curve, first between the mean and our z-score of 3.11. So we'll start in a positive direction first. In order to do that, I'll come down here to 3.1, over here to 1 on the top, and then where these two values intersect is my area under the curve on the positive side of this graph. We'll do the same thing in a negative direction. To find the area under the curve between our mean of 0 and z-score of negative 1.33 on this standard normal distribution, we'll look up the value of 1.33 on the table. So as a reminder, we can ignore that negative sign. So here we'll go to 1.3, going down the column, over to 3 to get us to 1.33. And what we'll see here is that we've got this value of 0.4082 where they intersect. So that tells us that we've got an area under the curve, or a probability of 0.4082 of getting an outcome between 0 and negative 1.33 z-scores. These values transfer perfectly over to our graph where everything is counted in days. Because each graph is the same except for the units we're counting in, we know that on this half of the graph we've got an area under the curve of 0.4991, and on this side of the graph we've got an area under the curve of 0.4082 shaded. In order to find our total final probability here, what we're going to do is we're going to add these two values together. So our two values, when we add them together, again we're doing 0.4082 plus 0.4991 to capture the entirety of this shaded area we have on the graph here. And I'm typing this into my calculator right now because I put my notes somewhere else and did the rest of this from memory, as I sometimes do. Okay, it gives us a final shaded area of 0.9073. In other words, the answer to our question here is that we have a 90.73% chance, or a probability of 0.9073, that we'll have a trial lasting between 3 and 7 days, because the total shaded area here on this graph is 0.9073. And that's the answer to the question.
Start out with the material for this week by talking about sampling. As you probably remember from the beginning of the semester, a sample is a smaller selection of members from a larger population, and it's typically that smaller selection of members that we actually are able to gather observations from. This is the data that we typically have in front of us. So how do we take samples, and how do we know that samples are going to provide us with useful information about those larger populations? We're going to start by talking about something called a simple random sample. This is considered the gold standard of sampling. A simple random sample is the kind of sample you want if you want to have a lot of confidence that the statistical methods you use are going to allow you to understand that population from the sample you took. In a simple random sample, every single member of a population has an equal chance of being selected into the sample. This works through two steps. The first is that you have to be able to list every single member of a population. If you can't do this, you can't have a simple random sample. The second step is to use some sort of random process to select members from that list. A random process could be the use of a random number generator. It could be a physically random process like Powerball Lotto. And so we have examples of simple random samples like the following. Jury selection is typically a simple random sample of registered voters. We have a list of every single person who's been registered to vote, and some sort of random number generating process selects members from that list. That gives us a simple random sample of that list of registered voters. Powerball, as I just hinted at a couple seconds ago, is also an example of a simple random sample. In this case, the list of every member of our population is the list of every single number that is on a ball in that big rolling ball full of balls thing. The random selection process used by the Powerball Lotto is the randomness of spinning a big ball full of balls and seeing which ones pop out the hole for the balls. So a Powerball Lotto also provides a simple random sample of the numbered balls within the big Powerball ball thing. If you can tell, I don't play the Lotto. I don't really know what I'm talking about here. But the process is a simple random sample. Another example of a simple random sample we could think of would be if you were to pick Skittles out of a big bag of Skittles. So in this case, you have a list of every single member of your population being every single Skittle in your bag. And if you pick out a Skittle, record the color, pick out another Skittle, record the color. As you populate a sample that way with a bunch of different recorded colors, in each case, each Skittle had an equal chance of being selected from the bag, even if the process was just, wiggling your fingers around in the bag. In this class, we're going to assume that all samples that we encounter are simple random samples. This is not going to be the case. So the class data, while giving a cross-section of students who are in these required classes in any given semester, is not actually a simple random sample. I didn't take a list of every single student in SCJ and randomly select members off that list to populate the sample. So it's not a simple random sample. We're going to generally, for the purposes of our examples, assume that it is. The general social survey, which you use for this first assignment and will use for future assignments, is also not a simple random sample. This is a sample that uses something called a multi-stage cluster design. It provides a representative sample of the population, but is not the truly gold standard of sampling. The reason that we're going to assume that all samples in this class are simple random samples and kind of pretend they are even when they're not is that as the gold standard of sampling, the simple random sample allows us to most cleanly use the principles of probability to understand the world around us. Our focus here is going to be on how that works and how we can use probability to generate information from samples. Methods like using a cross-section of students in a required class or using more complex sampling methods, as is in the case of the GSS, generally do a pretty good job of approximating information that you would get from a simple random sample. But the ins and outs of those processes are more a topic for research methods than they are for this class. So from here on out, we'll acknowledge that we're working with imperfect samples, but for learning these principles, we'll assume that they are better than they are. So why are simple random samples so good? Why are these the gold standard of sampling, and why are we going to pretend that everything we see in this class is a simple random sample? The key is that simple random sampling produces what we call a representative sample. And when a sample is representative, the following things are true. The characteristics of the sample can be expected to match the characteristics of the population that that sample was drawn from. In other words, the sample statistics, such as the sample mean or sample standard deviation or median, are expected to match the parameters, such as a population mean, population standard deviation, or population median, of that population they were drawn from. So this is a really, really useful characteristic. If we want to use a sample to learn about the wider world, in other words, to learn about a population, it's going to be really helpful to us that a simple random sample can be expected to match that larger population. Of course, if we're talking about simple random sampling, or any sort of process with the word random in it, we also have to be aware that random chance is operating. And as we've seen in working with probability so far, probability and probabilistic processes can tell us what to expect, such as expecting a sample to match the characteristics of a population, but they can never tell us exactly what we're going to find, because random chance is always operating. And so when we collect a sample, we can expect it to look like a population, but we can also expect to see differences that are just due to random chance. The reason that a simple random sample is so useful is that we can be confident that the only differences between our sample and our population are due to this random chance from it being a probabilistic process. And this is what will allow us to use statistical methods to take into account that random chance and come up with estimates with a sort of buffer around them for random chance. And with any sample that is representative, we can do this sort of thing. So as a quick example here, I have another type of sample that is not a simple random sample, but that is based in a representative sample, and that allows us to kind of think about samples and populations in this way. So political polls, like the GSS, like the class survey, are not typically simple random samples. They're often populated in different ways. But they are representative, meaning that we can expect the sample characteristics to match population parameters, aside from whatever differences we see based in random chance. In other words, polls typically allow us to collect data from a representative sample of American adults or American voters, whatever the target of that political poll is. And when we look at political polls, so for example, if we're considering percent support for one candidate or another, the representativeness of these samples allows us to assume that whatever percent support we see within the sample for a particular candidate reflects the percent support in the population. In other words, the sample statistics, such as the proportion of people who support a certain candidate, can be expected to match the population parameters, aka the percent of people in the population who would be expected to support that candidate. And with a well-constructed poll, and bit of a caveat here, polling is an imperfect process, and we have seen examples of polls giving non-representative data. But assuming we have a pretty good poll here that's representing the population well, any differences that we see between that estimate should be due to random chance. This allows us to account for random chance using statistical methods, and this is reflected in the margin of error that we often see when poll results are reported. So if you look at a result from a poll, you'll see 60% of candidates support, 60% of members of the poll support candidate A with a margin of error of plus or minus 3%. And this margin of error that you've probably seen before is in fact a statistical method for accounting for the random chance that creates differences between sample statistics and population parameters. So to sum all this up, a representative sample is one in which the sample statistics can be expected to match the population parameters. Simple random samples give us representative samples every time, but we can also approximate representative samples and achieve representativeness using other methods. And when we do, we can expect the characteristics of the sample to match the characteristics of the population, aside from random chance, which we can then account for by creating what we could think of as a margin of error. How does that work? Why is it the case that if you randomly select members from a population until you've populated a sample, such as picking members of a jury from registered voters, such as spinning out Powerball balls from the big Powerball ball until you have 6 of them, how is it that doing a process like this gives us a representative sample every time? Well, it starts with probability. And because simple random samples are based on probabilistic processes, what we already know about probability can explain how a simple random sample ends up being a representative sample. The first key point is that population parameters provide us with a probability distribution. And we're going to go back to the land of Skittles and M&Ms. And imagine, for instance, that you have a giant jar full of M&Ms, like a house-sized jar. It's really, really big. And 20% of that giant jar of M&Ms is made up of blue M&Ms. This gives us a probability distribution. Right? We know that blue M&Ms comprise 20% of the jar, so there's a 20% chance of getting a blue M&M anytime you pick a single M&M. And this is the equivalent of taking a bag of Skittles, counting up the different Skittles in the jar, and coming up with the probability of getting a particular Skittle anytime you pick it. So if we know the proportion of M&Ms that are different colors in our big jar, we can figure out the probability of getting an M&M of a particular color. So 20% of our M&Ms are blue. If you pick a single M&M out of that jar, there's a 20% chance that it's going to come up blue. As we also know, a probability distribution tells us what to expect after we repeat an outcome generating process multiple times and record multiple outcomes. And this harks back to that definition of probability as relative frequencies. Our probability distribution tells us what relative frequencies or percentages of outcomes we should expect after we actually repeat the process a bunch of times and record some data. So imagine we've got our giant M&M jar, and we pick an M&M out 100 different times. So we pick an M&M, record the color, pick another M&M, record the color, pick another M&M, record the color. We can expect, based on our definition of probability as giving us relative frequencies, that if we were to pick 100 M&Ms from our giant house-sized jar, 20% of those M&Ms should be blue. In other words, 20% of our outcomes should have come up blue if we had a 20% chance of picking a blue M&M each time. We can think of our 100 M&Ms that we just picked out of our jar as a sample of 100 M&Ms. So each time we picked an M&M, we were selecting a member from that population into our sample. So our sample here is made up of our many recorded outcomes, and probability told us what the proportion of those outcomes should look like. In other words, our 100 M&M picks are now a sample of 100 M&Ms. And because of these properties of probability, because we know the probability of getting a single blue M&M, that means we know the proportion of M&Ms that should be blue after we pick 100. That tells us the proportion of our sample that should be made up of blue M&Ms. And so following this logic through, the distribution of M&M colors in the population in our giant jar full of M&Ms gives us the distribution of M&M colors that we should expect in our sample. If our giant jar is 20% blue, we should expect through these processes of probability that our sample of M&Ms will be 20% blue as well. Except for that random chance that we mentioned before. So anytime we're dealing with probability, random chance creates differences between what we expect to see and what we actually get. In other words, even with a representative sample, even using simple random sampling, our gold standard, or another method that approximates it pretty well, we're still going to see random chance operating. And so we're still going to see samples that look different from populations just because of that random chance. And this is what we're going to have to take into account when we try to use samples to learn about larger populations. Because what I'm really saying here is that while we should expect our sample to look like a population, it's always possible that it's going to look really different just because of chance. And so we'd want to be cautious in drawing too many conclusions from a sample without taking that chance into account. Useful to us is that the extent to which our sample differs from our population is something that we can predict. And a key thing that allows us to predict it is the size of the sample. In particular, smaller samples have more sampling error, in other words, larger, more frequent differences between the sample and the population. And this is because a few unexpected outcomes can affect a small sample drastically. It only takes a few unlikely things happening to completely change the composition of a small sample. As an example here, we've got our giant house-sized jar of M&Ms, and instead of taking a sample of 100 M&Ms, this time we're going to pick only 10. We expect, based on the composition of our jar, that 20% of our M&Ms are going to be blue. We expect our sample percentage of blue M&Ms to match our population percentage of blue M&Ms. So if we pick 10 M&Ms, we expect 2 of them to come out blue. But let's say that 3 unexpected things happen. And we just so happen to get 3 extra blue M&Ms, 3 more than we expected. The result is that now 5 out of our 10 M&Ms are blue. We expected 2, we got 3 extra, so we've got 5 out of 10 M&Ms being blue. Now we have a sample that is 50% blue. And if I were to just look at that sample and say, well, based on this, my best guess for the composition of the jar is 50%, I would be way, way off, because my sample here is not doing a great job of matching my population just because of this sampling error, aka random chance creating a difference between my sample statistics and my population parameters. Larger samples, on the other hand, have less sampling error because it would take a lot of unlikely events to dramatically affect the composition of the sample. So let's imagine that instead we pick out 10,000 M&Ms. And this, by the way, is why we needed a house-sized jar, since that probably wasn't apparent until this moment. But we've got this really, really, really big jar of M&Ms. And now we're going to pick out 10,000 of them in a 10,000 M&M sample. Our probability distribution and principles of probability tell us what we should expect from our sample. We should expect that, just like the population overall, 20% of our large M&M sample is going to turn up blue. This comes out to 2,000 out of 10,000 M&Ms. So we pick 10,000 M&Ms, we expect 2,000 of them to turn up blue, aside from whatever random chance does. Now let's say 3 unexpected things happen. We get 3 extra blue M&Ms more than we were expecting. So this is just like in our first example, 3 unexpected outcomes. Now, instead of having 2,000 blue M&Ms, we have 2,003 blue M&Ms. As we can see here, our sample statistic still matches our population parameter pretty closely. With 3 unexpected outcomes, we get a sample that is 20.03% blue. And if I were to look at my large sample and say, well, my best guess for what the population looks like is 20.03% blue, I would be pretty close, because those 3 unexpected outcomes, which totally threw off my small sample, barely affected my estimate from my large sample, because they just kind of got overwhelmed by all of the expected outcomes that we got. What would it take for my large sample to be as wrong as my small sample? Well, the answer is about 3,000 unexpected outcomes. So you would have to be incredibly, incredibly unlucky, or I guess lucky, depending on what you're betting on here. But it would take some very, very unlikely events, 3,000 unexpectedly blue M&Ms, out of the course of those 10,000, to give us a sample proportion that is 50% blue. In other words, that's as wrong as what we got with 3 unexpected outcomes in our small sample. And the overall idea here is that with large samples, unexpected things tend to cancel each other out. You have a couple draws where you get extra blue M&Ms, they're probably going to be offset by a couple draws where you get less blue M&Ms than you would expect over the course of that 10,000. So our unlikely events even each other out, and they tend not to kind of throw off samples in this major way. And in order for a really large sample to give you a really incorrect estimate, you would have to be in the very, very, very small percentage of unlikely outcomes where you could, theoretically, get 3,000 more blue M&Ms than you expected just by chance. But it would be very unlikely. That's like winning the lottery unlikely. So our large samples tend to have less sampling error than our small samples, because in large samples, it takes a lot of very unlikely outcomes to create a lot of sampling error. Of course, I would be remiss if I didn't also talk a little bit about non-representative samples. So in this class, as I mentioned, we're largely going to be thinking about representative samples. We're generally going to be treating all samples as though they are simple random samples, the most representative of them all, the gold standard. But when you're encountering data in other contexts, you will often encounter data that's drawn from samples that are not representative at all. And this is an important problem because it can really affect the conclusions that you draw from that sample data. And here's an example for you. In the class survey, I asked you this question: do you favor or oppose the death penalty for persons convicted of murder? This is actually a question that I took from the general social survey that you used for assignment 1. And so I have 2 different samples, one of which is our class, which is largely representative of SCJ students, but probably not representative of the U.S. public overall, compared to a sample that's representative of the U.S. public overall. And we could imagine that what we really want to know is the percentage of people in the U.S. who support the death penalty. So let's compare our non-representative sample with our representative sample. In the class survey, we had a sample size of 64 and a breakdown that looks like this. In the class this semester, 69% opposed the death penalty, while 31% favored the death penalty. And if this was the only data I collected, my reasonable conclusion would be that most people oppose the death penalty. The issue, though, is that this is not a representative sample of the US overall. If we compare it to a very strong representative sample of the US overall, we see that our conclusion should be flipped around entirely. And if you ask people in the US overall whether they favor or oppose the death penalty, we'll see that about 60% favor while about 40% oppose. And the reason for these differences, and the reason that we would want to be very cautious about trying to draw conclusions about the US overall from the class survey, is that you guys do not necessarily represent the US overall. And members of this class are different in a couple important ways. The one that always springs to mind first that I think is the most important is that this class is far more educated than the US population overall. Only about 30% of people out there have bachelor's degrees, whereas every single person who took this survey is either getting a bachelor's degree or a master's degree. Students in the class also tend to be younger. We live in and around New Jersey, which is a blue state, more urban than the general population, often skews a bit more liberal, more diverse demographically, or in terms of race and ethnicity in particular, than the US population overall. And so what's happening here is that our class sample is not really getting views from people who have lower amounts of education, who live in red states and rural areas, people who have more conservative political views, people from places that are more overwhelmingly white, right? So there are these various characteristics that tend to be associated with attitudes about the death penalty, and because our sample doesn't have a fully representative sort of panel of people, we miss out on the views of the people who tend to have more positive views towards the death penalty. So in other words, our class survey gives us sample that is not representative of the overall population and results in a conclusion that would be wrong if we were trying to understand death penalty attitudes overall. And one thing to notice here too is that another difference between these samples is that the class survey is much smaller than the general social survey, 64 versus 2,067. And so many people's first thought when they look at these numbers is that, well, of course our survey didn't do as good a job of capturing death penalty attitudes because it's much smaller. We've got much more sampling error in the class survey. And while that is true, it is not the most important thing that's going on here. And the issue with non-representative samples is that no matter how big your non-representative sample gets, it can still be wrong because it's missing out on whatever swaths of the population are not represented. And an example of this comes, another example that switches around which one is bigger, the representative or non-representative sample, came from a presidential election many years ago, and we'll watch a quick video about that next.